Okay, so welcome to this session. My name is. So, welcome to this session. Uh, so, the first speaker, who's
Thank you for introduction, and I'd like to present a joint work with Radko, in which we dealt with some construction of aggregation function based on Möbius transform. The main motivation for our work came from decision-making theory, where one of the hardest tasks is the identification of a fuzzy measure. And this problem can be often be handled by considering another set function, which additively represents the wanted fuzzy measure. And this set function is Möbius transform. You probably came across this Möbius transform with some problems, as for instance, extension of fuzzy measure or extension of a Boolean function, which is defined on the vertices of the unit hypercube to the whole unit hypercube, when we often use Lovász extension and Ovenaka multilinear extension, which both are based on Möbius transform. I will start speaking about Möbius transform on general posets. Then I will focus on Möbius transform, particularly for a fuzzy measure, and then I will mention some recently introduced notion of Möbius product, which provides a wide framework for many construction of aggregation functions based on Möbius transform. So let's have a finite poset and a field with two binary operation. Here we misused the notation for standard addition and multiplication. And we can define so-called incidence algebra of k-valued binary functions, fulfilling the property that fxy is 0 whenever x is not in this order relation with y. We have two distinguished members of this incidence algebra. The first one is the Kronecker delta function, which is defined as 1 whenever x is equal to y and 0 otherwise, and the zeta function, which is defined as 1 whenever x is in this order relation with y and 0 otherwise. And we also can define a binary operation over this incidence algebra called convolution, which to every couple of functions from a P assigns another function, which is defined, as you can see here, as the sum of products of values of these two functions of fxz times gzy, where z is taken over, this sum is taken over all z's lying between x and y in our poset. It was mentioning that the Kronecker delta function works as neutral element with respect to this convolution operation, and together with convolution and the addition of functions inherited from this field operation, this AP forms a ring. And we can ask if there exists the inverse of the zeta function with respect to the convolution operation, and the answer is yes. And this inverse is called the Mobius function, and it can be quite easily shown that it takes this form, that it is equal to 1 whenever x is equal to y, and this is the inverse element of the sum of such values of mu, so it is defined recursively. The sum is taken over all z's lying between x and y and different from y whenever x is in the order relation with y, and it is 0 otherwise. With help with this Mobius function, two mathematicians, Weissner and Hall, independently discovered the general Mobius inversion formula for posets, stating that for two mappings from some poset with a unique minimal element to some field, this relation holds that n is additively represented by values of the other function e, where the sum is taken over all elements being less or equal to the argument of this n, when, even only if e can be additively represented by sum of products of n and this Mobius function. In fact, both of those guys worked at group theory, and they used this Mobius inversion formula for solving some problems in group theory, and they were not aware about consequences in other parts of mathematics. It was just 30 years later when Giancarlo Rota realized the consequences, when he deeply investigated the Mobius function, and he in his paper there were many of consequences in combinatorics, including inclusion-exclusion principle and some graph problems as coloring and flow problem. Okay, so with help of the general Mobius inversion formula, we can define for every mapping on the bounded finite poset to a commutative ring, so-called Mobius transform, and the dual Mobius transform is exactly those functions which additively represents the original function f. Okay, and now we come to the example which explains why this function is called Mobius, because it was in 1832 when Mobius, does somebody knows which what these two first letters stands for? Nobody? Nobody? Okay, it's August Ferdinand, I guess. Okay. Okay, so August Ferdinand in 1832 played in particular settings of divisor poset, which is when this order relation is just divisibility, and you can see that this statement is the particular case of the general Mobius inversion formula. And the original function, in fact, it was unary function, but it is our Mobius function, as I mentioned before, when the first coordinate is fixed at as 1. Okay. Now the example of particular importance for us is the Möbius transform of a fuzzy measure. So we have a Boolean lattice of subsets of some finite set ordered by inclusion relation, and in the role of the field, we take the set of all real numbers. And it can be easily shown that in that case, Möbius function, for instance, by using mathematical induction, we can show that the Möbius function in that case take this form. So for some set function, its Möbius transform is given by this formula, which is quite well known. Yes, we know it in this form, probably. And I can stress that the Möbius transform, as I already a couple times said, it's just a set function which additively represents the fuzzy measure. And in, no fuzzy measure, but so far it was just set function. But when we consider a fuzzy measure, it means monotone set function, which is grounded, and say it is also normed. So the value of the whole space is equal to 1. Then also Möbius transform sums up to 1. In terms of Möbius transform, some interesting properties of fuzzy measure can be represented. For instance, K additivity means that values of Möbius transform are 0 whenever this set, the cardinality of the set is greater than K. And also belief measure can be represented in terms of Möbius transform. The Möbius transform of a belief measure is non-negative for all subsets of M. Okay. Now, quite recently, just 2 years ago, Radko, Anka, and others introduced quite new notion of Möbius product of two real valued function defined on some poset, finite bounded poset, in fact, as you can see here, to a couple of such functions, we assign a real number given as sum of products of Möbius transform of the first function multiplied by values of the second one, when the sum is taken over all elements of the poset. Yes, so using the expression for Möbius transform, this can be represented also in this form. Yes, as I already mentioned in the introduction, this construction provides a quite large framework for different construction of aggregation functions. This is one of them. We can consider a Boolean algebra with fixed fuzzy measure and some set of set functions assigned to each point in the unit hypercube. And the authors defined some mapping A and G from the unit hypercube, defined at every vector x as Möbius product of M and corresponding Gx. And they investigated the question when this mapping is an aggregation function for every fuzzy measure. And they also found some necessary condition that in such a case, the function GE, which is defined as GXE, need to be an aggregation function. And it's interesting that when we work just with belief measures, non-negativity of Möbius transform of such measure gives us that that also AMG is as convex combination of aggregation function is also an aggregation function. Another interesting example is that when we take some fixed permutation and fixed fuzzy measure and a point in a unit hypercube and define two functions, as you can see here. The first one is a fuzzy measure of a particular subset, and the second one is just a sigma i's coordinate of vector x. Then using how a Mobius transform look or Mobius function looks on a chain, we obtain these two formulas, which are quite familiar because in the case that sigma, this permutation sigma is such that it orders this vector decreasingly, then this is just two formulas for discrete Shocker integral. Yeah. 12 years ago, again, Anka and others investigate a particular case of this construction, which is the construction when they investigated mapping FMA defined in this form, where this is, of course, Mobius transform of some fuzzy measure, and A is an n-array aggregation function applied to vector xe, which is related with the original entry, as you can see here, that we just fixed the coordinates corresponding to the set E, and others we replace by ones. And the particular cases are already mentioned, Lovaas and Owen extension. And this is, as I said, particular case of Mobius product construction. They found some characterization for binary case that FMA is an aggregation function for each fuzzy measure, even only if A is a distorted quasi-copula, and in higher dimensions, the A volumes of such rectangles, which are just touching some surface of the unit hypercube, needs to be non-negative. Yes, and now we come to a problem which we try to solve with Radko. The first one was this, that we considered not all fuzzy measures, but just two additive fuzzy measures. So we expected that the set or class of or suitable aggregation function which provides aggregation function FMA would be much larger, and it is definitely true, but we didn't succeed in full characterization. We have some quite simple observation about when boundary conditions are fulfilled, and that when we have the convex combination of suitable aggregation function also is a suitable aggregation function, and also when we distort entries, we again obtain suitable aggregation function, but we don't have full characterization. But this is quite interesting example that of a function which doesn't lead to aggregation function FMW when we consider all fuzzy measure, but it does when we consider just two additive fuzzy measures. I need to speed up a bit, yes. Okay. So unfortunately, we have very little results, so I'm almost finished. Okay, so the second problem was that we consider not aggregation function with fixed arity, but an extended aggregation function. And here, this vector is just restriction of the original entry vector to the corresponding subset. And we try to solve the same problem. Again, we have some quite simple observation. But this is quite interesting. This is an example of aggregation function. This is arithmetical mean, which leads to an aggregation function. And we probably can expect it naturally that this FMA is a linear combination of coordinates of entry vector, but it wasn't clear that the coefficients are non-negative, but we managed to show that they looks like this. So it's clear now that this is just a weighted arithmetical mean. So the consequence of this is that we have a method of how to make a probability measure from a fuzzy measure. Yes, we started with some fuzzy measure M and we ended with probability measure. And we also observed that taking the strongest, the weakest, or any symmetric fuzzy measure, we ends up again with arithmetical mean. As some concluding remarks, we also try to consider pseudo-arithmetical operation, which are in first case just generating from standard addition and multiplication, but it turned out that in such a case we don't obtain nothing new, that all results from the standard case can be also transformed into this pseudo case. But what is quite promising direction of the future research is to consider a possibilistic Möbius transform, and maybe there will be some interesting results. So I just presented two open problems, and this is what I wanted to say. Thank you for your attention, and here are some references. Thank you very much.
There is any quick question? So I have a curiosity. So you said that from the fuzzy measure you make a probability.
Because the coefficients of weighted mean sum up to 1, so it's just probability.
But you can in a way control how you make the probability from the measure.
Sorry?
You can control the way that. What I did not understand is it is kind of automatic. So given the measure, you get just the probability, or you can in a way tune.
Yes, it's just yes. Those are those coefficients. So those are these like values of probabilities. Yes. Okay.
So we move to the next question. Next session.
Sorry. Jsem to stala.
I start?
Yes.
Okay. So, Mr. Chairman, ladies and gentlemen, I intend to present results which were obtained several years ago and they were published. And I would like to use the fsta opportunity. Despite that the author of this contribution is Martin Papcho, there are another authors, and this paper was elaborated with my colleagues, and I hope that friends from Pamplona too, two of them are here, Javi and Joshua, and hopefully Umberto is watching. And what was the problem? There are many situations in which there is necessary to consider not only one-dimensional data input, but it is necessary to consider multi-dimensional cases. And an author usually writes, there are many applications and so on in which you can use these results So hopefully, I would say at least there are 3 of them. And color images, deep learning, and multi-expert, multi-criteria decision-making. First one, each color image can be represented via triples. When you consider red, green, and the blue channels, so in that case, you have to handle triples, let's say RGB triples. And if you consider more than 3 channels, that's the case of deep learning. You have to think and handle and carry out n tuples. And the third one example is when you have several experts and they estimate one alternative or another one. So they say that this is better than another one, and they estimate it via real values. So in all of these cases, you have to handle with multi-dimensional data, which are presented in the form of multi-dimensional matrices. For the case of one-dimensional vector, sequence of real numbers was elaborated, I so call it, infimum supremum middle approach. The representative output is choose like it is middle of deviations which are negative, and from some point of view is the best, and the another one border lays on positive outputs, and the tool to measure how far away is the input from the output which is looking for is deviation function. I will recall the definition later. So my goal is how this approach could be extended to the matrices, and based on extended definition to build a method which can handle this multi-dimensional deviation functions. And it's quite natural to expect that the output will be again multi-dimensional, or for example, some vector of real numbers. And well, we are here because fuzzy is in our hearts. And so sometimes our life is restricted just only to unit interval, but there are many applications, again, in which there is necessary, or at least it's better from technical reasons, and from it's better to understand the situation, not just only values from unit interval. So this method was elaborated even for those cases. Throughout my presentation, I will be devoted to denote close interval of real numbers. And I think there's no need to recall basic notions of aggregation theory. So let me recall a deviation function notion. It is a function from square of real numbers, again into reals, and in the second factor, so it means the first variable is fixed, it is continuous and strictly increasing. and the deviation of the same numbers equals 0 every time. And quite a typical example is the function given by this formula, y minus x. The graph in a 3 Euclidean space is a plane, and the intersection, so when x is fixed, is straight line, and in the plane of x and y axis, the graph is diagonal. Because of technical problems, because of mathematical reasons, and other ones, there are several papers which consider why and how to do it. The function, deviation function, was improved, and it was leaded to Darotsi means. So if d is a deviation function, a mapping MD from vector of real numbers into reals is said to be Darotsi mean if and only if this function is given by formula. It means that the representative output is the solution of this equation. So the sum, they can be negative and positive at the same time. The sum equals 0. So from some point of view, the output, desired output, is some sort of the equilibrium point. And another improvement is called a moderate deviation function. In the second factor, in the second variable, is non-decreasing, and in the first variable is non-increasing, and again, it is equal 0 if and only if the inputs are equal. And again, the prototypical example is the same as I've already described before. Now, trick is very simple. And I was surprised that it could be published and it has applications, and from some point of view, it's better than the others. But well, really simple. Each real matrix can be viewed as a sequence of real numbers. So you can write down row by row, entry side by side. And since you can apply moderate deviation functions on the real vector, you can almost the same way apply it for real matrix. So this is the proof, and the theorem is here. And well, as you can see, just what was done for one real vector, it is done for matrix, and the output is average of those two boundary values. And so the function MD, which is defined for real matrix X, is an idempotent symmetric aggregation function. And this exactly could be used to fuse data, real data. Well, when I was thinking about this problem, I needed some support. It was clear that couldn't be beer. So I have decided chocolate could be fine, and it has occurred that, well, it's fine. And since in Czechoslovakia, Czech Republic and Slovakia, still is very popular chocolate, which is called student seal, I've decided to present the method here via chocolates. So as I've already said, one application is connected to RGB color images. So from some point of view, each such information consists from 3 layers: blue layer, green layer, and red layer. So in fact, you can see behind these chocolates 3 matrices: blue, green, and red matrices. So the matrix in question consists from 3 matrices. And now there is possible from different point of view to consider the same matrix. And when you are watching from up, you see the matrix of triples, RGB triples, and in general case, matrix of real n tuples. There are more n channels. So it's back. Step 1, to take account that the information is in the form of multi-dimensional matrix. Step 2, divide each layer, each sub-matrix into the same, for the sake of simplicity, square matrices. And of each of them, it will be applied moderate deviation function, which is defined for some matrix. So each of these square submatrices will be fused, resulting in some real value. Now, symbols. In some situations, that is necessary to consider that each entry can have different weight. So it's not a problem to consider here weights. And by the similar way, define a weighted deviation based matrix aggregation function. And so for some problems, there is enough to consider that each layer, each submatrix has the same weight as it is in the case of experts. Each expert has some weight. It is or he is or he's not so important. So another version, each layer can have a different moderate deviation function. And so the output is some sort of matrix, and it consists from n tuples of fusion. You can imagine that it's quite simple to consider not just square submatrices, but different shapes and so on. And the method is generalization of the one-dimensional case. In the paper I have mentioned, there was tested method, and it was used. The function given by this formula is quite popular, and many of you knows them. So it has occurred that it is, from some point of view, better in some indicators, but I don't know about it. So if you really interested in, ask Joshua or Javi. Even in this case, it doesn't make sense to fuse matrix, but it's better to fuse preference vector and then the row. And I think it's already time. It has occurred that it is possible to apply it even in motor imagery brain computer interfaces, and that was published in this paper. And for those of you really wants to taste the method, I've got some multi-dimensional support. So please. Okay.
Are there any questions? No? I have a question. You mentioned having different size, submatrices of different size. I don't understand.
This need not to be just square, rectangular. It could be.
So you will have in the same.
Yes,
In
the
the
same
same
manner.
chocolate, different pieces of
Yeah,
different
yeah.
size. This means.
Like here, not
Yeah.
squares, but well, rectangles. Yes,
Yeah.
no problem. And
Thanks. So, next speaker.
In the few minutes, I want to tell you about some generalizations of Schocker integral and its application that I'm working on with my supervisor, Lenka Halchinova. I will present two problems and their solution using two types of Schocker-like integrals. The first problem is image impairing. The goal is repair damaged areas or remove unwanted objects, for example, text from the image. In 2000, authors of first cited paper introduced algorithm based on a derivative of image. And the main ideas of its method is follows. The first is necessary to create a mask of image where pixels denote areas for repair. The key of image inpainting is to apply color from outside to the inpainted area along the isofolds. Isofolds are curves that connect the pixels at the same brightness. This ensures that the inpainted color is correct. Isofolds can be obtained by using gradient of image at the given position, and subsequently the smoothness of image can be estimated by Laplacian, which also indicates the inpainted color. This inpainted color is multiplied by a small constant, and this value is added to the color from previous iteration. In addition, each 15 iterations is applied anisotropic diffusion for a better estimation of isofolds. As part of our research, we focus on possibility of replace gradient and Laplacian by another concept using non-additive measure and integrals. we proposed algorithm with following ideas. Let gray denotes mask of image and white other pixels of image. The numbers express the color in grayscale. If given pixel is on the border on a mask and it has at least 4 neighbors, we consider the absolute value of differences, the central pixel and mentioned neighbors. We get the values and these values are scaling and normalized and adjusted some way, but notice this important. This we get in final whites, and these whites express the importance of corresponding colors in image. These colors are multiplied by whites, and we get the vector for aggregation. It appears that aggregation should not depend on range of components on vector. Therefore, we always permuted vector in a non-decreasing order for permutation. The following question is by which functional to aggregate this vector. We can use, for example, average, median, Choquet integral, maximum, minimum, etc. Or question is, it's possible to use all of them? The answer is yes, we can use the sequence of aggregations and assign them weights. These aggregations we can also arrange in non-increasing order, and whereas we're looking for the Choquet-like operators, the weights can be represented by difference of two monotone measure two sets. We get the special case of on permutation dependent operator. This definition is very important, the sequence of aggregations and sets of permutations. In other words, each vector has in set of permutations its own permutation. First permutation relates to components on input vector, and the second permutation relates to aggregated values. This second permutation also relates to the sets for monotone measure. For aggregation, we use the concept of conditional aggregation operators introduced in third cited paper. It's a map that is monotone with respect to the conditional set, and the second condition say that if input vector has 0 components with respect to the conditional set, that then the value of conditional aggregation operators is also 0. This concept has several interesting properties. For example, conditional aggregation operator does not have to be monotone on full basic set, but only on subset. Or conditional aggregation operator with respect to the basic set is standard aggregation function. And if we need to arrange only, aggregate only some components of vector, we don't need to change its dimension. And by suitable formula of conditional aggregation operator, permutation and input vector and various conditional sets, we can generate several standard aggregations. For example, using this formula, if conditional set is basic set, we get arithmetic mean. Or if conditional sets are of this type and input vector is arranged in a non-decreasing order, we get the median. We can also get minimum, maximum, etc. aggregations functions. The second question is why on permutations dependent operator? The first reason is that is computationally efficient and experimentally achieves good results. This concept is generalization of concept introduced by Bocek and Kalushka in cited paper. And in this concept is only one permutation, and this permutation is always non-decreasing. In addition, they use standard aggregation functions, and in our concept, we use conditional aggregation operators. Operators of Bocek and Kalushka cover some other concept as twofold integral, Shocke integral, standard Shocke integral, MC integral, etc. The motivation for introducing on permutations dependent operator relates to the standard fuzzy integrals. Standard fuzzy integrals have has permuted input vector in a non-decreasing order, and this permutation relates to sets for monotone measure. For formulating various formulas for function connecting the input vector, permuted into vector and monotone measure, we get now integrals as Sugeno, Shilkred integral, standard Shocke integral, etc. Now we have permuted vector that is aggregated by conditional aggregation operator, and this values is also aggregated by other, permuted by other permutation. And using this formula for function L, we get our own permutation dependent operator. Okay, let's back to impending. We create vector for aggregation, and we aggregate it by our Shocke-like operator. In a formula for Shocke-like operator, we use three types of conditional aggregation operators with respect to various suitable conditional set according to the dimension on the input vector. For this vector, you can see on the slide, we can aggregate value, which is multiplied by constant 1 or -1, and also by a constant delta, which achieves origin impending methods. This value is added to the previous iteration, and we get the impeded image. On the next slide, you will see 1,200 iterations with anisotropic diffusion applied each 15 iterations. We get following result. As you can see, the text is removed. The idea replace gradient and Laplacian with generalization of Shocke integral is inspired by of six-sided paper, which relates to edge detection. In this paper, authors dealing with fuzzy logic-based methods or of edge detections. Their methods is follow. First is to necessary transform image to grayscale and blurring in for radius of noise. Then for each position of pixel, it's consider the absolute values of differences central pixel and its neighbors. It creates also 8 components vector. These values are arranged in a non-decreasing order and aggregated by generalization of Shocke integral. This aggregation detects edges. These edges are further scaling and binarization for final detection. This procedure, as part of our research, we modified in following. We don't arrange the values of vector in non-decreasing order, but we preserve information about position of pixels. Inspired by Sobel operator, we assign a weight to each neighbors of central pixel, and we aggregate vector by generalization Shocke integral with respect to the modified monotone measure. The second concept I want to short present of generalization Shocke integral is Shocke integral based on family of conditional aggregation operators. Family contains operators with respect to the set from collection. Collection is subset of power set, and important is that for each set from collection, there is exactly one conditional aggregation operator. Then we can define Choquet operator based on conditional aggregation operators. This improper Riemann integral of generalized survival function. Generalized survival function for each non-negative alpha express monotone measure of complements of sets under which conditional aggregation operators achieves values greater than alpha. In a discrete space is the graph of generalized survival function is step function. If conditional aggregation operator is maximum and collection is power set, the generalized survival function is equal to the standard survival function, and thus Choquet operator based on family of conditional aggregation operators is equal to standard Choquet integral. Relations between generalized survival function and standard survival function we deal with 8-cited paper. Okay, for aggregation or for edge detection, we use Choquet operator based on family of conditional aggregation operators with various families of conditional aggregation operators and standard Choquet integral according to the fourth blurring of image. We get the result. We can compare qualitatively or quantitatively, and we get a better result than all standard gradient-based method for edge detection, a better result than was said in the mentioned paper. Okay, on this slide we can see edge detection of probably most famous image in imaging processing. This is standard Kenny edge detector based on gradient, and further it's detection by Choquet operator based on family of conditional aggregation operators. Okay, in image impairing and edge detection, we use most important property namely average behavior operators. We focus on the assumption under which conditional aggregation under which Choquet integral based on family of conditional aggregation operators and operator dependent on the permutation lies between minimum and maximum input vector. This is very important because we aggregate the colors and output must be always color, and this must be in the scale of color. Okay, and this property is also equivalent for idempotency. Then we guarantee that if we aggregate the same color, that also aggregating value represent this color. Okay, these operators have other important properties. For example, the first operator is monotone with respect to the input vector and monotone measure, but the second operator not, etc. Okay, and finally, the natural question is relationship between mentioned operators. We focused or we show that the equality occurs not only for simple input where your function is 0, but also for non-trivial case. Thank you for attention.
Are there any questions? To me, when you define the phase, you define all this, and then you define the measures. In some of them, the measure is fixed or not, or did I understand it correctly?
Measure fix where?
When the variations of the Choquet integral.
No, measure is monotone measure.
Yeah, but how do you select that?
Please.
How do you select the measure?
Also, measure from its in edge detection is related to Sobel operator and matrix in Euclidean space.
Okay, thanks. So we move to the fourth talk. Thanks.
Okay, so good afternoon, everyone. My name is Tomasz Józefiak, and I work in the research group with Michał Boczek, Marek Kałuszka, and Andrzej Okolewski. And today I will be talking about an extension of the Socket integral for multi-valued data. We know from the previous presentations that multi-valued data is often the case to be somehow aggregated. And also we have been shown that the Socket integral is indeed a tool to do so. And since the atmosphere in this conference is very great for me, I decided that I want to tell you something about myself. So I am a PhD student. And also in 2020, I won a bronze medal in the World Championship. And during my presentation, you can think in which sport it was. And at the end, I would like to tell you about it, if I do not forget. So you are more welcome to make a guess. But it will be only after I go through all of these 3 points. So first of all, let's start with a definition. This is the standard Socket integral. Some of you may be a little bit surprised, but I don't think so really, because we often deal with the Socket integral for the input, which is not the continuous function, which is the vector, for example. But here is the continuous function. And what's important, and I would like to point out in this case, that the Socket integral itself generalizes the expected value, because the expected value may be described in this way if mi is the probability measure, but here we deal with a non-additive measure. There are some generalizations of the Socket integral for non-negative, for real valued functions, and we would like to focus on this particular case, where here we have the dual measure. There are some other generalizations, but we would work on that due to its genuine properties. And we have introduced a new concept of the Socket integral, which would allow us to integrate the multi-valued data, which would be represented by n functions and would return a single scalar output. So here is our generalization, which comes from this work. And for n functions, we define the Socket integral, or in short, CH integral, as in the pattern number 3. So here summation goes over all of the binary sequences. And this part over there is as in the formula number 4. We have proven that it doesn't really matter if I use the strict or non-strict inequalities over there, that this integral is indeed well defined, that which means that I can put this function into the Lebesgue integral. And why did we choose that? Well, because it generalizes the concept of the expected value of the product of these functions. If mi becomes the probability measure, then we would get the expected value of the product of functions f1 to fn. And of course, for if we put the n equals 1, then we would recover the standard Socket integral. And I would like to also point out that this formula we would get for the n equals 2, because later on it would be used for some other formulas and operators that we have introduced. Of course, we often the case is when we deal with the discrete space. And for example, putting a discrete space in our definition of the Socket integral for n non-negative function gives us the 5th formula. And the 5th formula was introduced in this work, where we had to aggregate some input, in which we have the level of believedness of these values indeed to be the one represented by this vector. So we had this set of vectors and we aggregated them. In this work, it was shown and used. So I would like to point out some properties of the CH integral, and only 3 of them, but of course many more. So if we deal with a fuzzy measure, which is presented if the mi of x equals 1, then our integral is an averaging aggregation function, because the aggregation function are of a lot of importance in this multi-valued data aggregation. It satisfies also comonotonic additivity and monotone convergence theorems and Fatou's lemma, and some of other properties of the standard Schottky integral are also preserved, while others are preserved with some additional assumptions. Sugeno have provided an outstanding result, which allows us to compute the exact value of the Schottky integral, and we have shown that it could be also applied to our integral. So if we deal with this measure, which is called the disordered measure, then we can get a formula which is only the one variable integral on the right side. So we can replace the double integral with a single valued integral. And here we proposed an open problem because we have done it for 2 functions, f and g, and we didn't do it in the general case for n functions. So here is an open problem. Also, because some of the computations of the CH integral are really hard, we proposed some of the inequalities of them. First of all is Schwarz inequality. The second is Jensen inequality, of course, with some additional assumptions. The third is the Markov-like inequality. And the last one is this exponential inequality. But what's important is in the last one that on the right side, we have the standard Schottky integral. It is not the concept that we have introduced. It is the standard because here is a single function. There are no commas. Yeah. And let me move on to the applications of the CH integral. So in this presentation, I would like to give 2 applications. And first of them would be, well, we know that if we deal with a probability measure, then, well, we are allowed to do a lot. But sometimes the case is that we have only the monotone measure, that is, the additivity is not satisfied. And we have a non-additive measure. And therefore, we can apply the Markowitz method of stock portfolio selection. That imagine if we have a 1 monetary unit and we want to invest it. So the case would be to maximize the expected return over some of the risk level, which would be represented as this sum of covariances. And our task would be to find this vector x1 to xn. But we do not have the covariances formula for these 2 variables, which are the functions indeed. And some of the proposed covariances formula and variances formula were the works of Sugeno and Jager. So the formula number 8 was proposed by Sugeno, and in terms of our notation, it is derived in this way. And Jager proposed these 2 formulas for covariance and for variance. And they are described in that way in our notation. And our idea, we proposed two ideas, but I would like to only show one, the better one, is to define the covariance formula as the pattern number 11. Some may say that it is very close to what Jalger has done, but let's look that here is the single Shochet integral. There is no comma, but here is a comma and it changes, well, a lot. And it uses, of course, our notation that I have provided at the very beginning. And of course, dealing with the probability measure recovers us with the standard covariance and variance formula for the variables, random variables. Some of the properties of these two are also satisfied. The number 2 only is for non-negative numbers, but number 1 and number 3 are well known also for the standard covariance formula. And the second application would be the problem of finding the average. Of course, there are some ways to do it, but it is important problem when dealing, for example, in the valuation of swap contracts, where we have to replace the sequence of non-deterministic quantities with a sequence of deterministic ones. And to do so, we would like to use the tool that we have introduced, and this is the way to do so. So dealing with a discrete space X, we want to find the average of n vectors. And to do so, by the means of the CH integral, we can consider the equation number 13. And due to some of the properties that we have put in our work, the right side of this formula may be easier written and therefore may be easier to calculate. And this is also the common idea that we want to solve this equation to find the average value, because it would preserve all of the necessary conditions. For example, the average value of the same vectors would be the same vector, and many more of the properties. And this equation, of course, always has at least one solution. And if we want it to be determined in the exact way, the only one solution, then we can restrict to some subset of our space, or add additional equations to the equation number 13. So yeah, this was our idea to introduce and deal with the formula number 3, which would generalize the concept of the expected value of the product of n variables, random variables. And we have used this definition number 3 to do so. So this is all from my side. Thank you very much for your attendance and for your time. And are there any questions?
So
Okay.
you compare your covariance with Sugeno's covariance, and then you had some proof here of your covariance. This does not hold in Sugeno's. Or what is the main difference besides of the comma that you already mentioned?
Okay, so all of the covariances of Sugeno, of Jager, and two of us were different between each other. So they satisfy some other properties, and you may choose which of them you want if you want to preserve some of these properties.
But in a way, if we are thinking on the standard in statistics,
okay.
then what do you think that it would be the best? Yours or the others?
It's hard to say, but if the me becomes the probability measure, then all of them are the same. So
that's clear.
we cannot It depends of your applications and of which properties do you want to be to hold, because none of them hold.
And then I have another question. You mentioned in one of the first slides the case of n equal 2, and you have these two that are positive and two that are negative. But if you have three, this kind of I don't know, symmetry also hold.
Yes. If n equals 3, then I would have 8 of them, and some of them would have the minus sign and some of them plus, and the minus sign would always occur where it is a dual measure. Because this is the Heffing type of the covariance, I would say, if we add also the second part of that.
Okay, thank you very much.
Well, thank you very much.
Question? No? Okay, thank you. So then we move to the last. Yeah.
Okay, so it was the sport called ice swimming, and it consists of swimming during the winter on the cold water. And I won a bronze medal on the 100-meter backstroke on that. So.
Thank you. So my name is Josef Poč, and this is joint work with Radek Halas from Palacký University of Olomouc. And I would like to speak about Sugano integral compatibility and its relation to distributivity. So maybe majority of you know this formula. It represents Sugano integral, which is defined on the real line or on the unit interval. And as you can see, there are used two kinds of operation. One is supremum, and here is minimum. So there are many generalizations of this kind of integral. One type is to use different operations. Yeah. So different operation of supremum and different operation of minimum is used. So, but the domain is still real interval or real numbers. Another generalization goes beyond real intervals and is made on bounded distributive lattices. This was introduced by Jean-Luc Marichal in 2010, and the main idea behind this extension is to replace operations of maximum or supremum in this case and operation of minimum by the corresponding lattice operations of lattice supremum and infimum of meet and join. So I recall this definition. If we have lattice valued fuzzy measure mu, which is defined, I will speak about discrete Sugano integral. So we have a finite space consisting of n elements, and we have L-valued fuzzy measure mu, which goes from power set of this set to the distributive lattice L. So as in real valued case, this fuzzy measure is monotone, and measure of empty set is equal 0. Here 0 means the bottom element of the distributive lattice, and the measure of the whole set is equal 1, and it is the top element of the corresponding lattice. And the corresponding formula is the following. So it is taken join over the all subsets of these terms. Here is infimum of the corresponding fuzzy measure of this subset, and the meet of all values which are from corresponds to this subset. Yeah. So this is also known as a disjunctive normal form. And as you probably know, in a real valued case, there is disjunctive normal form, and this also works in the case of distributive lattices, and this form is in the following form. Yeah. So maybe the main question is why distributive lattices? Yeah. So as you see, these formulas can be used and in arbitrary lattices. So the main question is why distributive lattices are used. So maybe one of the answer to this question is because for distributive lattices this works really fine. Yeah. And what is the aim of this talk? To show at least some reasons why it is fine to work in distributive lattices. Yeah. One reason is because we have two equivalent formulas for this Sugano integral, and if we are not in distributive lattices, they are different. Yeah. So they do not coincide. So this is maybe one reason. Yeah. So I recall some basic facts about distributive lattices. So lattice is distributive if it satisfies the so-called distributive identity, and it is one of these two identities. If one identity holds in a lattice, then automatically other one also holds in this lattice. Maybe one of the most important results about distributive lattices is due to Marshall Harvey Stone, and it says that distributive lattices have sufficiently many prime ideals. So I recall what is a prime ideal. So ideal, it is a subset of a lattice which is downward closed and closed to the operation of join. And this ideal is prime if the following condition is satisfied, and it whenever we have two elements, mid of which belongs to the P, then at least one element belongs always to the P. Yeah, so this is primality of ideal. And to be more precise, what does mean that distributive lattices have sufficiently many prime ideals? So if we have a distributive lattice and two different elements A and B, then there is a prime ideal which contains exactly one of A and B. So given any two different elements, they can be separated by a prime ideal. Yes, and this is one of the crucial property of distributive lattices. This is behind the well-known Stone representation of Boolean algebras as a algebra of sets and also as Birkhoff representation theorem of distributive lattices as rings of set, for example. Okay, so what is the basic property of Sugeno integral in this setting? It is that Sugeno integral extends this L-valued fuzzy measure. What it means, if we have a fuzzy measure mu, then the following holds. This means that if we compute Sugeno integral from the tuple which consists, which is the characteristic function of the subset S, then we obtain the measure of the subset S. Yeah, here characteristic function is defined in a natural way that if E belongs to S, then it has value 1. 1 means the top element of the lattice L, and if E doesn't belong to the subset S, then it has value 0, which represents the bottom element. Yeah, so this means the characteristic function. Yeah, so here is the simple computation which shows that this holds. So if we have, and if we compute the Sugeno integral of these characteristic functions, then this formula can be divided into two parts. One, we take supremum over all subsets of S, and then all supremum over the all subsets which are not subsets of the set S. Yeah, and this part always attains value 0, because here at least 1 0 appear. So all this takes 0. So supremum of zeros is 0. Yeah, and here we have infimum or meet of the whole ones, the top element, and it is intersects with the value of the measure. Yeah, so these parts attain this only this value, and as this measure is monotone, supremum of this values is the largest value, so it is mu of S. So this is really easy computation. So this is one of the basic property of Sugeno integral. So now I will recall axiomatic characterization of the Sugeno integral, which was given by Marischal in the mentioned paper from 2010. And this integral was characterized as a weighted lattice polynomial aggregation function. What it means, class of NRE weighted polynomial functions is defined as follows. If we have any k, then any constant is considered as such a polynomial function, and also kth projection is also polynomial functions in this way. And if we have two NRE weighted lattice polynomial functions, then their join and their meet is also weighted lattice polynomial function. And all such functions are constructed by finitely many applications of the previous two rules. So here is one example. If C, B, and D are constants, then these are the expressions of these kinds. Yeah, if these are nothing else than terms over the lattice operations, and also constants can be used. And every such term naturally defined functions on a given lattice, and this lattice function is denoted due to Marshall as weighted lattice polynomial function. So, and the basic characterization of the Sugeno integral on a distributive lattice is the following. Sugeno integral is the unique weighted lattice polynomial function which extends given fuzzy measure. Ooh, okay. Now I will relate this topic of Sugeno integral to the so-called compatible functions. So I recall that an equivalence relation on lattice L is called a congruence relation if it is compatible with lattice operations. Yeah, this compatibility and notion of congruence is one of the key term in algebra. So it is a basic notion. So what this means that congruence, that the relation is compatible with the lattice operations. Whenever we have this relation, we have two elements A and B, which are related under this relation, and we have two elements C and D, which are related under this relation. Then also, if we applied operations, so you can think about that as if we have two equations, we can sum these two equations. Yeah, this is something similar. So this means that the operations, that the relation is compatible with the lattice operations. Yeah, so and only equivalence relations which are compatible, they are congruences. Yeah, okay. So if we have NRE function, then it is compatible if for any congruence relation theta, if we have n relations, ay is congruent modulo theta with by, then also applying these functions to these tuples, we obtain that the result is also congruent under this relation. Yeah, so this is some kind of generalization of these two equations. Yeah. Okay, so now examples of compatible functions. Obviously, constant functions are compatible. Yeah, it is nothing to verify. Also, projections are compatible. And lattice operations are compatible because they appear in the definition of congruences. Yeah, so it is natural that they are compatible. And it is not difficult to show that if we have compatible functions, then also composition of these compatible functions is again compatible. Okay, so compatible functions are closed under the composition, and from the algebraic point of view, they form the so-called clone. Yeah, and this clone is very important in algebraic study of structures. So we have the following relations. These four examples of compatible functions means that all weighted lattice polynomials are compatible. Yeah, it is not difficult to show. And these, in general, case of lattices, these weighted lattice polynomials are form subset of monotone compatible functions, and in some cases, or there can be also compatible functions which are not monotone. For example, if we have Boolean algebra, then the operation of negation is compatible, and obviously this is not a monotone operation. So in general, we have such inclusions. Okay, so what is the key property of compatible functions on distributive lattices? And it is that compatible functions uniquely extend a given fuzzy measure. Yeah. So assume that we have a distributive lattice and two compatible functions f and g, and consider element A from the nth power of this L such that fa is not equal to ga. So then we know that distributive lattices, for distributive lattices, there is a prime ideal which separates these two values. Yeah, this is a consequence of Stone theorem. So we can assume that, for example, fa belongs to P and ga does not belong to P. Then we can define Boolean element. It is element which coordinates are equal to 0 and 1 in the following way. If a y belongs to P, then we define bi equal to 0. And if bi does not belongs to P, then we put bi equal to the top element, to y. Okay, so in this case, it is not difficult to see that ay and by are congruent by theta p, where this theta p is a congruence determined by this prime ideal. Yeah, if we have prime ideal, then one can define that two elements are congruent if they both lie in this ideal P, or simultaneously they do not lie in this ideal P. Yeah, and this primality ensures that this relation will be a congruent relation. Yeah, and now we have property of compatibility, and this means that as ay is congruent with by, then fb is congruent to fa, and gb is congruent to ga. And consequently, we obtain that this Boolean element bold b distinguishes these two functions. So this is precisely what was mentioned in the up in the slide. As you can obtain here in this proof, distributivity was not used explicitly, only in the form of Stone theorems that any two elements can be separated by prime ideal. Yeah, so this assertion is also true in the lattices where any two elements can be separated by a prime ideal. Yes. So okay. So what is the consequence for Sugeno integral? If we have an L-valued fuzzy measure mu, then Sugeno integral is of this form. As you can see, this is use are constants and lattice operation, so it is compatible functions. And as it was shown, it extends the measure mu. So this compatible extension is unique. So we obtain another characterization of Sugeno integral. If we consider distributive lattices, then Sugeno integral is the unique compatible function which extends the fuzzy measure mu. Yeah, and this unique extension property is very important. So natural question can be asked whether there are other types of lattices where this unique extension property also holds. Yeah. So for this, consider this property which is related to a bounded lattice L. If we have two n-ary compatible functions, f and g, then from this property, if they agree on a set of Boolean elements, then they necessarily agree on the whole lattice. Yeah, this is extension property which was used in the previous slides. Okay, so assume that we have a bounded lattice, and if it is distributive, we know that due to Stone theorem that it have prime ideal separation property. Yeah, and as we have seen on the previous slide, if it has prime ideal separation property, then it has unique extension property. So assume that unique extension property holds for the bounded lattice, and we can consider the distributive identity. So this is identity, and we can denote this ternary function on the left side as f, and this ternary function on the right side as a g. Yeah. But 0 and 1 as a subset of L is distributive sublattice. So for all Boolean elements, this equality holds, and consequently, if we assume that this lattice has unique extension property, then necessary fx must equal to gx for all triples of this lattice. And necessary, this gives that this lattice is distributive. So we have shown the following chain of implications, that distributivity implies prime ideal separation. This prime ideal separation implies unique extension property, and this unique extension property implies distributivity. I recall that this implication is the well-known famous Stone theorem, but I will remark that it holds only in under the assumption of axiom of choice, yes, or some equivalent or maybe some weaker assumptions are needed. Under if axiom of choice is not considered, then it can happen that we have Boolean algebra with no prime filter or prime ideal. So no two elements can be separated. Yeah. So this implication really heavily depends on axiom of choice. Okay, this was shown in this presentation, and this implication that prime ideal separation property implies distributivity was known due to Iseki, who proves it in 1952. However, our proof goes in another spirit. So this was proved if L is bounded. However, if L is not bounded, then this implication can be also obtained from our result, because if we add a new bounds, if we have lattice which is not bounded, we can add a new bounds 0 and 1, and then this lattice L will have prime ideal separation property if and only if this new lattice will have this property. But here we have a bounded lattice, so this property implies distributivity. And L is a sublattice of this L star lattice, so this is necessary also distributive. So our results also show this Iseki result in its full generality. Okay, so this is all what I want to present to you. So thank you for
Are there any questions? A quick question? Yeah, please.
You talk once expected. And result. Yeah. Oh, no. It's good, that's spoken part. So if we forget about exponential and so on, it is possible to show that distributivity is equivalent to what?
I'm afraid about this. This. Yeah, I'm not sure. I think that I don't know, but I think that probably it will be not possible. But I don't know. I'm not expert in models of set theory to show but
It's only concerning algebraic things without models here, because we are formatting completely algebraic the question. So
yeah, but this proof is based on the fact that you can separate, yeah, and some equivalent, maybe some equivalent form of this if it will be used, but I don't know.
yeah, in fact, it's the question of whether work is equal to fsta.
Yeah.
Yeah.
Yeah, it is. Yeah,
Yeah.
but I
It's the
don't.
same.
It's the same. Yeah, but I don't know.
It's-
I don't know.